Our focus so far has been to describe relativistic collision between particles. As an example, we looked at the annihilation of an electron and a positron into a muon and an antimuon, but that's only one example of fundamental process. We have plenty others. This one clearly requires relativity because the mass of the muons is about 200 times the mass of the electrons. Therefore, the electrons and the positron have to be relativistic in order for the collision to be able to have enough energy to produce the muons and the antimuon. It's clear also that because the particles are relativistic, the interaction is very fast. The particles interact with each other during a very short time. If the particles were non-relativistic, however, because they have a much smaller velocity, they will spend more time near to each other, and therefore they might have more opportunities to interact. They could even form a bound state. Of course, to form a bound state, the interaction will have to be attractive, or there should be an external potential trapping the particles together. If we have a bound state between two particles, nothing prevents to have also a bound state between three particles, four particles, etc. This is what we call a quantum many-body system. Examples include the nucleus made of nucleons, electrons inside the atom or in a molecule, atoms themselves inside the macroscopic molecule or an atomic cluster, or in a cold atom system, in a gas, in a liquid, etc. For such a many-body system to be bound or simply to have enough particles interacting with each other during a long enough time, the particles need to have a small energy. This means, of course, they are usually non-relativistic, but also this means that we often don't need to describe explicitly the mediator between the particles. Either the mediator is massless, in which case they travel at speed of light, and that means almost instantaneously for as far as the non-relativistic system is concerned, or they are much heavier than the typical energy scale involved in the system, in which case we can integrate out the associated field for the mediator. In the first case, we saw that this leads to an interaction which is in 1/r, a long-range interaction, while in the second case, it leads to a contact interaction. In the low energy limit, we usually also can't produce pairs of particles and antiparticles, and as a result, the number of particles in the system remains constant. Finally, at low energy, we can also often neglect the internal structure of the particles, if they have any. That's because at low energy, the particles have a large de Broglie wavelength compared to their internal structure. For instance, the nucleus is made of nucleons, and the typical kinetic energy scale and potential energy scale of the nucleons inside the nucleus is of the order of a mega electron volt, but we will need something like a giga electron volt in order to probe the internal structure of the nucleons in terms of quarks and gluons. Similarly, if we take a system of cold atoms, we are probably talking of kinetic energy of the order of the milli-electron volt. That has to be compared with the internal excitation of electrons going from one shell to the other inside the atom, and that is of the order of the electron volt.